really common one is the standard penetration test, the SPT.
SPT. Okay. What does that involve?
We basically drive a standard sampling tool into the ground at different depths, and we count the hammer blows needed to drive it at a specific distance.
Okay, counting blows.
Yeah, and those counts give us what we call N values. These numbers tell us a lot about the soil's density, how loose or compact it is. And that helps us estimate its strength, its bearing capacity. It's like taking the soil's pulse, in a way.
So a quick snapshot of resistance at various points. What if you need more detail, like what the layers actually are, or need samples to test back in the lab?
Good question. That's where soil sampling and borehole logging are critical. We drill boreholes down, sometimes quite deep.
Right.
And as we drill, we collect samples. Some are disturbed, meaning their structure is altered, but others are undisturbed, which we try to keep as intact as possible for lab tests.
Oh, okay.
And crucially, we keep a detailed log, a borehole log recording the different soil types, layers, rock, and importantly, where we hit the water table.
You mentioned another one, CPT.
Yes, the cone penetration test, or CPT. It's a bit different. Instead of hammering, we push a cone-shaped probe steadily into the ground.
Pushing.
And this cone has sensors measuring tip resistance, friction along the side, the sleeve friction, and the water pressure in the soil pores. It gives us a continuous stream of data as it goes down.
So more like a continuous EKG than just a pulse check?
That's a good analogy. It gives a really detailed profile. And then for very direct bearing capacity, especially for things like shallow foundations, there's the plate load test. We literally load a steel plate on the ground surface and measure how much it settles.
Okay, so you're physically testing a patch of ground right there. Makes sense. Now, you mentioned collecting samples, taking them back to the lab. What happens there? That sounds like where the real deep dive happens.
It definitely gets more detailed. So once we have those soil samples, we run a battery of tests. One of the simplest but still vital is just finding the moisture content. How much water is in there?
Seems basic, but important, I guess.
Very. Then we do things like the Atterberg limits. These are tests for the liquid limit and plastic limit.
Liquid and plastic limits, what do they tell you?
They help us classify fine-grained soils, like clays and silts. They tell us at what moisture content the soil transitions from behaving like a solid to a plastic putty to a liquid. Understanding if it might shrink, swell, or lose strength when wet.
Ah, okay. So how it behaves with water.
Exactly. And then, really critical are the shear strength tests. These measure the soil's ability to resist sliding or shearing forces. Think about a slope failing, or the soil under a foundation being squeezed outwards. Shear strength tells us how much force it can take before that happens. It's about the soil's internal friction and cohesion. Hugely important for foundation design and slope stability.
Incredible detail just from soil samples. But like you said, the site is more than just soil, right?
Yeah.
What else needs checking before excavation?
Absolutely. Observing the groundwater table is key. Knowing its depth is critical for planning the excavation. Understanding if we'll need dewatering systems pumps to keep the hole dry, which can be a major operation.
Right. Digging into water is a whole other challenge.
A big one. And then there's the topographic and utility survey. We need to map the site's contours, note any existing buildings nearby, but crucially, locate all underground utilities.
Ah, like gas lines, water pipes, electrical cables.
Exactly. Hitting one of those during excavation is, well, it's bad news. Dangerous, costly, causes massive delays. So knowing exactly where everything is buried is non-negotiable for safety and just keeping the project moving.
So wrapping this all up, what this really means for you, walking past a construction site, is that every single building, big or small, relies on this hidden blueprint, this invisible investigation work we've been talking about.
It really does. It's an entire hidden world of engineering, ensuring that what gets built stays built safely.
Makes you appreciate what goes into the structures we use every day.
It does. And, it raises a bigger question, doesn't it? What other hidden complexities, what unseen layers of knowledge and effort underpin the world we interact with daily? Things we just take for granted that rely on this kind of careful, hidden work. It makes you think.